Howdy. This video is on intermolecular forces. Physical properties of materials like melting point, boiling point, vapor pressure, viscosity, surface tension, capillary action, cohesive forces, adhesive forces, solubility are determined by intermolecular forces. Intermolecular forces are the forces between molecules. After watching this video, you should be able to understand the importance of intermolecular forces. You should be able to understand how all intermolecular forces are electrostatic interactions. You should be able to put the different intermolecular forces in order of increasing strength. You should understand how intermolecular forces affect different properties of compounds. And you should be able to relate viscosity, surface tension, capillary action, cohesive forces, adhesive forces, and solubility to intermolecular forces. And so we can ask ourselves, why is nitrogen a gas at room temperature and water a liquid at room temperature? And the reason for it is that the interaction between the water molecules is stronger than the interaction between the nitrogen molecules. And so we can think about phase transitions as a competition between intermolecular forces and kinetic energy. And also remember that temperature is a measure of kinetic energy at the atomic level. And so if you have weak intermolecular forces, then you're going to have low melting points, low boiling points, because you don't need a lot of kinetic energy to overcome those intermolecular forces. The stronger the intermolecular forces, the higher the temperature you have to raise to cause something to either melt or vaporize. So intramolecular forces are the forces that hold atoms together to form molecules. So that would be like covalent bonds. Intermolecular forces are the forces between molecules, between ions, or between molecules and ions. Intermolecular forces are much weaker than intramolecular forces typically. And so if you think about a covalent bond, that's a couple hundred kilojoules per mole. Most intermolecular forces are less than 20 kilojoules per mole. But again, intermolecular forces determine boiling point, melting point, vapor pressure, solubility, viscosity, surface tension, and capillary action. And so if we think about solid benzene, remember the blue corresponds to a partial positive charge and the red corresponds to a partial negative charge. And so if you look carefully at the video, you'll see that the edge of one molecule is facing the face of another molecule, optimizing the electrostatic attraction between the two. And again, the stronger the intermolecular forces that hold the solid together, the higher the melting point, the more heat you have to add to get the solid to melt. Intermolecular forces hold water molecules to form ice. And so it's kind of interesting. Ice has a fairly open structure. It's one reason why, well, it is the reason why the density of ice is less than that of water, which is fairly unique for ice. Now this time bar, I think, is 1 picosecond. A pico is 10 to the minus 15th. And so you can see that there's always motion at the atomic level. Even at 0 Kelvin, there's going to be motion. There's always going to be vibrational motion. Intermolecular forces hold water together. And so as you go from the ice to the liquid, you do reduce the amount of intermolecular forces. But in the liquid, you still have the intermolecular forces. In water, you have hydrogen bonding, and they're indicated here by the dashed red lines. And so the stronger intermolecular forces in a liquid, the higher the boiling point and the lower the vapor pressure. Whenever you have a liquid, some of the liquid is going to escape into the gas phase, and that's going to produce the vapor pressure. The stronger intermolecular forces, the lower the vapor pressure. So strong intermolecular forces between molecules, more kinetic energy is needed to overcome the intermolecular attraction. The higher the melting point, the higher the boiling point, and the lower the vapor pressure. The more similar intermolecular forces, the more soluble two liquids are. And so often we use the phrase likes dissolve likes, indicating that if two things have very similar intermolecular forces, they will be miscible in each other. And miscible just means that you can form a homogeneous solution in any ratio. Now, carbon tetrachloride and water are immiscible because their intermolecular forces are very different. Hexane in water, immiscible because intermolecular force is very different. Carbon tetrachloride and hexane, miscible because they have similar intermolecular forces.
Nonpolar carbon tetrachloride is poured into a test tube. When the nonpolar colored solid is added, the solid dissolves in the carbon tetrachloride. When polar water is added to the test tube, it forms a layer on top of the carbon tetrachloride, since water is immiscible with and less dense than carbon tetrachloride. When nonpolar hexane is added to the test tube, it forms a layer on top of the water, since hexane is immiscible with and less dense than water. When the test tube is vigorously shaken, the two nonpolar liquids form a single layer at the bottom of the test tube, and the polar water layer sits above this layer.
So it's kind of cool. What's going on is that, we saw that these two were immiscible. These two are immiscible, so they form these different layers. And so at one point we had carbon tetrachloride, water, and then the hexane. And then when it was shaken, the hexane and the carbon tetrachloride formed one solution because their intermolecular forces were very similar. Now we can see the same thing if we're looking at oil and water. Oil has one type of intermolecular forces, water another, and so the two are immiscible.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
And so the way you can think about it is that, we have a solvent, and so we're going to have solvent-solvent intermolecular forces. We have solute intermolecular forces. And to cause something to mix, you're going to have to replace these intermolecular forces with the solvent-solute intermolecular forces. Now in this case, the interactions between the water molecules are too strong, and so these will not replace those interactions. And so water and oil do not mix. And so again, we mean likes dissolve likes is that if they have similar intermolecular forces, then they should be soluble in each other. And again, miscible means that liquids are soluble in each other in all proportions. Immiscible means that liquids are not soluble in each other in any proportion. Im is Latin for not. Now, alcohols contain an OH group. And so it's going to be kind of similar to water. If you remember, it's going to be polar bond. And water also has H2O, so you have OH groups. And so you might think that all alcohols should be miscible in water. But it actually depends on how long a chain the alcohol is.
Colored water is added to ethanol, butanol, and hexanol. Water is miscible in ethanol, but not in butanol and hexanol. Butanol has a shorter carbon chain and is less hydrophobic than hexanol. This causes butanol and water to separate more slowly.
And so if we look at the structures, on top we have ethanol, and so we see the OH is a large proportion of the molecule. And if you look at butanol and hexanol, the OH is a smaller proportion of the molecule. And so if you had just, a carbon OH, it's going to be miscible in water. But with this long chain, that's going to be immiscible in water, like we saw in the video. Now it's kind of interesting. You also use what's referred to as surfactant molecules. And so surfactant molecule has a polar head group, and that part's going to be miscible in water, and a non-polar part that's not miscible in water. It's immiscible in water. And so these are used in detergents, and the idea is that the oil will be dissolved by the non-polar group, and then the water will see just the polar group on the outside, and so it'll make the oil actually soluble in water.
Surfactant molecules exist in aqueous solution as micelles, clusters of surfactant molecules. The long nonpolar chains of the surfactant molecules are pointed inward, and the polar charged end groups point outward into the water. In solution, water molecules interact with the polar negatively charged ends of the surfactant molecules and with the sodium cations that provide charge balance. When a microscopic oil particle on an item of clothing is exposed to this solution and there is agitation, the surfactant molecules become embedded in the oil droplet through the hydrophobic, oil-loving hydrocarbon chain part of the molecules. As more and more surfactant molecules become embedded in the oil droplet, it is lifted from the surface of the clothing. This process occurs because the polar, charged ends of the surfactant molecules interact strongly with the surrounding water.
So kind of cool. Surfactant molecules have two ends. One that is nonpolar, that's going to be attracted to the oil, and the other is polar, that's going to be attracted to the water. Now, intermolecular forces also lead to things like surface tension. And the way of thinking about it is that, so if we have a liquid here, and say we have some molecules on the surface and some molecules in the bulk. Now, if you have strong intermolecular forces, remember, the stronger the traction, the lower the energy, the more stable. That means that the molecules in the center of the water are going to be more stable than the molecules at the edge of the water. And so liquids will try to minimize the amount of surface that it has, and that's referred to as surface tension. And so surface tension results from the surface of the liquid being as small as possible, because again, the bulk liquid will have more intermolecular forces, stronger attraction, lower energy, more stable.
A paperclip is placed carefully in water, or rather on it. The metal clip floats because it isn't heavy enough to break the water's surface tension. By adding a small amount of soap, we reduce the water's surface tension. The paperclip sinks.
And so again, the surface tension is just due to intermolecular forces. And again, also, intermolecular forces are why liquids form droplets.
You think nothing exciting would happen, you think it would just go like this. But what we'll see is much more interesting.
All right, let's drop it.
What we've got here are water droplets, which look pretty ordinary at normal speed, but at 2,000 frames per second. Maybe mathematician John Bush can explain to us just how a drop can bounce.
Whoa, whoa, whoa. That is so cool. And that's just going to float all the way over to here. Oh!
Okay, so you're saying that happens all the time?
That's right. Every time a water drop coalesces into water, so every time it rains, a raindrop hits a puddle.
Rains. That's raindrops in a puddle.
Yeah, so that's billions of times a day. Why does the droplet sit without just connecting?
So there's an air layer in between the two, and it's basically it'll coalesce as soon as the drop makes contact with the bath, but it takes a finite amount of time for the air layer to drain.
Or for non-PhDs, there's a thin layer of air separating the drop from the water. But as the air is pushed aside, most of the droplet connects with the water below. But this happens so fast, the connection is actually pinched off, and a smaller droplet is formed. But why do some of the drops leap up into the air?
When it coalesces, waves are generated at the point of contact, and they sweep upwards, and they apply a force, which lifts the drop off the surface.
And then once again, it's surface tension. It has enough force that it pulls itself back off.
That's exactly right.
A tenth of the size.
This surface tension is the quality of a liquid that causes the surface layer of that liquid to behave like an elastic sheet. It's the effect that allows insects to walk on water and water drops to hold together.
Wow, that's crazy. How great it is. That's amazing.
This cycle happens again and again until the droplet is small enough to be completely absorbed.
Try to get one.
And all again just because of intermolecular forces. The stronger the intermolecular forces, the stronger the traction, the lower the energy, the more stable. And so it's kind of interesting. So we know that liquids form these droplets, form spheres. Sphere is the shape that has the lowest surface area per unit volume. Now you kind of wonder, well, how big of a drop can you get?
That's kind of cool just to watch them move. Okay, there.
And so this is done on the space station.
This side, here we go.
And you can get this huge drop of water just because there's no gravity.
Wow, I just love those oscillations. Here we go. Okay, let me switch it to a black background. Yeah, so that's about 800 mils. So this should put it around 1100 milliliters. Let's see what happens here. Oh, I just love that. Look at that. Amazing. Just one of these jaw-dropping moments. Okay, here we go to do it again, looking into the camera. Big puff. Here we go. Oh, right at the lens. I saved the lens. What I'm planning to do is, after this whole series of experiments, I'll suck all this water up with a syringe, I'll put it back in bags, and I'll use it to make tea with, so I'll end up drinking my experiment. You gotta conserve your resources when you're in a frontier. You don't get to see this as common, intuitive observables on Earth. And so when we go into a frontier, our normal Earth-honed intuition no longer applies. And this rule works when you go to the bottom of the ocean or into the stratosphere or wherever you find your frontier under the stage of an electron microscope. Your normal everyday life intuition no longer applies. And that's why frontiers are rich in discovery, because things aren't the normal, they aren't the usual. Joe, come take a peek at this.
Holy crap.
Get my towel ready to catch the satellite drop. Here we go. Isn't that wild?
That's great.
It's a superposition of surface waves that go around the outside of the sphere and body-centered waves, inertial waves that go through the middle. I'm going to give it another puff just because I'm in space and I can. And instead of putting a puff of air on it, I'm going to put a puff of water. This is going to have a lot more momentum in it than the air. Whoa, whoa, I was afraid. Oh, look at that, cool. I squirted water through. Oh, isn't that cool? The water in the sphere went around the air cavity and formed a huge bubble. Wow. Oh, that is so cool. Let's see what my hand looks like. Oh, look at that. Yeah, oh. There we go. Yeah, that's good. That's good. Shows that optics works. And let's see what my mug looks like. Oh. I can be a human pendulum. This shows the lens lock. Motion is in the opposite direction and the image is inverted or upside down. And there I am, and I'm going to come up here with my eyeball. Now I'm going to do the same thing with my nose, and this is going to get ugly, and I apologize in advance.
So it's really kind of cool. The water stays together just because of intermolecular forces. And so you could have a drop as big as someone's head if you have no other forces around.
Background, so I'm just a floating head. Okay, enough of that. And let's get back to doing some science.
So surface tension depends on the strength of intermolecular forces. And again, the water inside is going to be more stable than the water at the surface. And so the amount of surface is minimized. Viscosity also depends on intermolecular forces. Now it doesn't just depend on the strength, but you can actually think about if you have oil, you have a long chain of alkane, and so sometimes those molecules can get a little tangled in each other.
The viscosity of a liquid depends on the strength of its intermolecular forces. Glycerol has relatively strong intermolecular forces and is rather viscous. Its resistance to flow is high. Ethanol, by contrast, has weaker intermolecular forces. It flows easily and has low viscosity.
But again, I think the movie has a little bit wrong. It's not just the strength intermolecular forces, but if you have much larger molecules, they can kind of get tangled up in each other, reducing the ease of flow, increasing the viscosity. Intermolecular forces actually lead to capillary action and to the existence of concave and convex meniscuses. And so here we have a concave meniscus. And what this actually means is that the attraction between the liquid and the surface of the container is stronger than the interaction between the molecules in the liquid. And so cohesive forces are interaction between the water molecules, interaction between the liquid itself. Adhesive forces are interaction between the glass, the liquid, and the glass. And so if the adhesive forces are stronger than cohesive forces, then you get a concave meniscus trying to maximize the adhesive forces. Now, if the adhesive forces are weaker than cohesive forces, you get a convex meniscus. So like if you have mercury in a glass tube. And so adhesive forces are kind of cool. You know, a gecko can walk up the wall can walk up a wall just because intermolecular forces. This is actually a robot gecko. And so in general, intermolecular forces are fairly weak. But if you have enough surface area, you can actually have animals walking up walls. And so you can also look at the angle between the droplet edge and the surface, and actually is related to the strength of the adhesive forces. And so the bigger this angle, the weaker the adhesive forces is to the cohesive forces. And so if you have a coating on the lens, if you have no coating, then the water kind of goes all the way on the surface. If you use a coating, sometimes you can actually make it so that the water does not want to be on the surface. And so on this side of the glass, a coating was added to make it hydrophobic, water hating, and so the water does not stay on the surface. And you can either add a coating to the surface or you can change how the surface behaves. Now this side of the glass was not treated, and you'll see that the water stays on the surface. And so the petri dish on the right was treated, the petri dish on the left was not treated. And so you can imagine maybe this type of technology would be helpful for making it easier to clean dishes, to make it so it's easier to see through the windshield of a car. Also, in terms of solar cells, they use this type of coating to try to keep the solar cells clean, so the efficiency doesn't get reduced. Now, capillary action is when you have strong adhesive forces between the liquid and the solid.
When a piece of paper is dipped in water, the water moves up the paper by capillary action. The attraction of the water to the surface of the solid paper allows the water to rise against the force of gravity.
That's kind of cool. You can also use what's referred to as chromatography. So if your solution had different types of molecules in it, often the adhesive forces would be different for the different types of molecules, and you're able to separate out some molecules based on the capillary action. And so all intermolecular forces are based on electrostatic interaction. And we saw electrostatic interaction follows Coulomb's law. The bigger the charges, the stronger the attraction. The shorter the distance, the stronger the attraction. And so if we think about intermolecular forces, of these, ion is the strongest, and you can think about that as whole charges, and so it's a strong attraction. Ion dipole, the dipole moment is not going to be a full charge, and so it's a little bit weaker. Hydrogen bonding is a special form of dipole-dipole, which is stronger than dipole-dipole. And then you have dipole-dipole-dipole, induced dipole, and then dispersion, which are all relatively weak. And so you can think about these, ion just means you have interaction between two ions. Ion dipole means you have interaction between an ion and polar molecule. Dipole-dipole means a polar molecule. Dipole-induced dipole typically means a polar molecule and a nonpolar molecule. London dispersion, which is also referred to as induced dipole, you can think about as nonpolar molecule, but everything actually experiences London dispersion. And so polar molecules have dipole moments. That's why when we see dipole, we think polar molecule. And a nonpolar molecule can be induced to have a dipole moment. And that's why we say induced dipole interaction. And induced dipole is also referred to as London dispersion. I'll use those two terms interchangeably. And again, of these, ion is the strongest, then ion dipole, dipole-induced dipole, and London dispersion is the weakest. And so to understand how strong the interaction is, we have to know what the interaction is. And so we have to know, is it an ionic solid? Is it a polar molecule? Is it a nonpolar molecule? And so again, a lot of physical properties, melting point, boiling point, vapor pressure, solubility, viscosity, are determined by intermolecular forces. The stronger the intermolecular forces, the more kinetic energy is needed to overcome the intermolecular forces. The higher the melting point, higher the boiling point, and the lower the vapor pressure. I hope that was helpful.